My name is Colin Mykelti Wilson from St. Angela High School, Bandung. I'll be giving a compacted rundown of my research. This paper aims to find polynomial approximations for the arc length of a parabola, specifically in the case where calculators are not available. Solving for the arc length of a parabola can be done so using the following formula. The arc length, capital L, is equal to the width of the parabola segment multiplied by some constant that ultimately depends on h, which is simply the ratio between its total height and width. This h metric is useful, for if two parabolas share the same h value, they are similar in shape and differ only in size. The reason for this paper is that the original formula is difficult to use and unintuitive. For starters, the existence of square roots and logarithms would mean that the aid of calculators are needed to perform this calculation. Alongside that, an exact value, while true, might not be the most useful. People would not be able to tell at a glance what the true value in decimal actually is, which is arguably more useful for practical applications. When finding these approximations, the following criteria are taken into consideration. First, they must only contain the four basic arithmetic operations of addition, subtraction, multiplication, and division. Second, it must not require calculators or lookup tables, and as such, it prohibits the use of logarithms, fractional powers or roots, and trigonometric functions. Third, large exponents are not advised so as to keep efficiency. And most importantly, it must minimize error as much as possible while maintaining ease of use. Research is done quantitatively. The quantities in question are the errors of each function. In conjunction, two different types of approximations, Taylor series and Pade approximants, serve as points for comparison. To start, this process is split into two parts. First, generating the approximations, of which the methods differ depending on which functions are at play. First, the method of asymptotes. Let's take a look at a graph of the original formula. Notice how it approaches the line 2x for large inputs. If we add a second term to correct for this deviation near zero, we arrive at this equation. We'll refer to it as k. Second, error-correcting functions. In order to maximize the accuracy of k, an additional function is appended to it, reducing its error along a certain range. And lastly, Taylor series and Pade approximants are generated by matching a certain order of derivatives at a certain point. In total, this paper compares each functions of order 2, 4, and 6. Second part is analyzing the approximations. Analyzing each formula is done with the help of the online graphing calculator Desmos. Every approximation's error is plotted and then divided by x, or normalized, in other words, making it so that the error is proportional to the input size. By observing the function with the lowest average error along a certain segment, we can piece together several functions, minimizing the error across a broader range. These compound functions are called piecewise approximations. Now, for the results. Bear with me here, there's a lot to unpack. The k approximation we took a look at earlier is shown on the left. The bottom left contains the 5 best error-corrected functions, which when stringed together form the piecewise approximation, the error graph of which is shown on the right. Yellow lines mean an error of 0.1% and 1% respectively. Below it are the errors of Pade and Taylor approximations, and the bottom right contains the exact error figures for when these formulae are tested across two scenarios. More in-depth information about this can be read in the paper. In conclusion, the piecewise approximations are the best compromise between accuracy and ease of use, though as they consist of several different functions, it can make them hard to memorize and may lead to confusion among users. For general use, k is the easiest to calculate, while being moderately accurate across all inputs. This is very useful if you want to approximate something off the top of your head. And lastly, the Pade and Taylor series are the best use cases for this scenario. They are only accurate for small inputs, and even then, their complex nature means that most people will stick to the exact formula anyways. For future work, improvements include improving accuracy, comprehensively searching for the best error-correcting formula through software, and perhaps similar approximations for other algebraic splines. These are the references used in this work. That is all from me here. Thank you for tuning in.